Alright, so this is lecture 26 on Cartesian triple integrals. That's basically page 286 to 295 of my lecture notes for 2020. And so this is really just a natural continuation of the double integrals we've already talked about. First of all, if you had just an integral over a cube, you just do the integral over like the x, the y, and the z in an iterated fashion. But what's more interesting, of course, and we already see one. I think I already did one of those in the previous lecture. But if we had an integral where the region was interesting, then essentially what you want to do is to set up a system of inequalities which describes an arbitrary point in the region, and then you do an iterated integral according to that set of inequalities. So here's an example. Find the volume of the region between z equals y squared and the xy plane bounded by x equal to 0, x equal to 1, y equal to 1, and y equal to minus 1. So the idea here is dv is dx, dy, dz, so we can integrate the volume element to give the volume. And the inequalities which describe the region are 0 is below, and y squared is above z, and x and y are governed by these so-called rectangular bounds, and that's it. And so we have to integrate z first. Let's see here. What did I say? We must integrate with respect to z either first or second, right? The z integral can't be on the outside because we can't have the variable bound on the outside, essentially. So here's the way I set it up. I put the z bound in the inside, and then I did the now that there are three bounds, this links to the z, this links to the x, and these bounds link to the y. That's the way we can think about it. All right. And again, corresponding to what was given in the problem, see, y goes between minus 1 and 1, x goes between 0 and 1, and z goes between 0 and y squared. So then we do that integral. And that gives us, so the z integral just integrates to z, and then you evaluate z from 0 to y squared, you just get y squared. All right, and then we integrate from 0 to 1 dx with respect to x. Well, that just gives us xy squared, which again just evaluates to y squared. And then integrate dy, well, that gives me 1/3 y cubed, and from minus 1 to 1, well, it's going to give me 2/3 as my answer. So the volume of this interesting region up here is actually 2/3. Another example, we can consider the cylinder x squared plus y squared equal to 1, and z equal to 0 bound the shape below, and the plane z equals x plus y plus 1 bounded above, and we can call that solid B. So here's a picture of it. And so if you look at that, we have, of course, 0 is less than, so like the 0 and x plus y plus 1 provide a bottom and a top for z. And then if we want to think about 0 less than x squared less than y squared, x plus y squared less than 1, we can, we could picture that directly, right? That's a circle, right? I mean, actually, it's a disk. And so, like, this is y equals to the square root of 1 minus x squared, right? And this down here is minus the square root 1 minus x squared, right? And you notice that we're going between x equals minus 1 and x equals 1, right? So the way I think about this kind of process is, here's how I think of it. I think of first taking all of three-dimensional space, all right? And I think about slicing out the plane the half slab between -1 and 1. All right. And then I think, okay, well, that's still not the shape, right? Then I think about, okay, I'm going to take that slab, and then I'm just going to cut out this cylinder from it. And I do that by limiting y to be above the blue and below the y, below the red curve. And that gives me an infinite cylinder. And then I'm like, well, it's still not the volume. So then I cut it at z equals to 0, and I cut it above at the plane. And by that system of cuts, I start with R3, and through applying these inequalities successively, I cull the shape, the space down until I get to the region. So you have to think about all the three inequalities have to come together to work in unison to describe the volume, all right? And it's a bit of an art form to understand it, all right? But you start working, you work a few of these problems, eventually you'll get to it, but it's not easy, okay? Like, you need to work examples and check yourself, and just keep trying to understand what it is that's slipping past you. We all fight with slightly different issues on this material, but so I decided to integrate x over that volume, which I just called b. And so remember, we came to the inequalities which describe that region. I'll write over here, starting with -1 less than or equal to x less than or equal to 1, right? And then minus the square root of 1 minus x squared less than or equal to y less than or equal to the square root of 1 minus x squared. And then finally the final cut, 0 less than or equal to z, right, less than or equal to, and what was the plane? It was x plus y plus 1 equal to z, right? So this set of three inequalities just collectively describes x, y, z being an element of the volume. So once I've described the volume by a system of inequalities like that, then I can set up the iterated integral in turn. And so I integrate from 0 to the plane, right? And then my y is bounded by x in that way. And then, of course, my x goes between -1 and 1. So this is the order the integral has to be done for this description, like it's not optional. The variable bound that involves two variables has to be the innermost bounds. And if there's a variable bound which involves one variable, then that could either go here or here depending on what else is going on. But in this one, it has to go there, and then that. So, yeah, and then you can do that integral. You can iterate that integral, and I may or may not have the work here to do it. Oh, look. So, yeah, lovely. And the integral is a trigonometric substitution. It's kind of beastly. Eventually, I get to pi over 4. So it turns out this integral can be done much more elegantly using cylindrical coordinates later. So I'm not even going to, I would argue, I mean, you can glance at that calculation, but I would encourage you to wait and try to do that problem again later using cylindrical coordinates. It's way easier with cylindrical coordinates because that problem really suggests a cylindrical approach because it's based on a cylinder. Here's another one. B bounded by the coordinate planes. I'm pretty sure that's it. Planes. And the plane passing through these 3 points, right? So basically, the region we're talking about, it's got these 3 points. Well, I've drawn 4 points, but these 3 points. That's 1, 0, 0. This is 0, 1, 0. And this guy up here is 0, 0, 1. And, so also the coordinate planes. So it's essentially the region that has this as its top, and then like these guys are the bottom and the back of it, so to speak. It's a solid region. I figured out that the equation, so what I'm doing here is I'm looking at some vector v goes from where's that? Let's see if I can picture it. V goes from base point 0, 1, 0 to the top. So this is v, and w goes from 1, 0, 0 to the top, I think. Wait a minute. no, that one goes from the top. I'll get it eventually here. Yeah, okay, I think this is W. So if we take the cross product of V and W, that gives us the vector which is perpendicular to that triangle, that triangular slice of the plane. So that's a normal to the plane. In other words, the plane that we're dealing with here is x plus y plus z equal to 0, or excuse me, equal to 1. Or you can solve it and get z equals to 1 minus x minus y. That's an equation for the top faceplate of this, if you will. And of course, you can check this equation, right? If you plug in x equals to 1, you get x equal to 1 and y equal to 0, you get z equal to 1. Is that right? No, you get z equal to 0. If I put x equal to 1 and y equal to 0, it gives me z equal to 0. If I put y equal to 1 and x equal to 0, I get z equal to 0 there. If, if I put, so this is the point 1, 0, 1, 0, it checks. And if I put x and y both 0, I get z equal to 1, which is that point. So all three of these points satisfy this equation just as a check on our work. All right? Anyway, point is I've set up the volume, and then I do like I did last time. I say, okay, so to describe this volume, I need a set of 3 inequalities which jointly describe the volume, jointly describe the shape, right? The solid. And so for this one, I've got 0 less than x less than 1, all right? So, like, just to foolishly try to picture this, so this first one cuts the space into an unending slab, right? Like that. This is x equals to 1, and x equals to 0 is on the back, and this goes on, right? That limits me to just a slab of space. It goes on and on every which way. And then we say, okay, well, 0 is less than y is less than 1 minus x. Well, 1 minus x is, you know, in the plane, it's this line right here, right? But that corresponds to like some kind of like slicing. And y equals to 0 is, well, it's like this and this. So then you're taking this, you know, infinite plane, and now you're slicing it to an infinite wedge that goes on and on. All right, with this 0 less than y less than 1 minus x, and then finally the cutting by z. Well, that says it puts a bottom. It says z equal to 0. You know, is the base of this thing. So it says basically z equal to 0 is maybe it's this piece down here, right? This is z equal to 0 here in my picture, just to draw it bigger. So it puts this as the bottom of the shape, and then it puts z equal to 1 minus x minus y as the top of the shape. And so I won't try to draw it; it'll make it too ugly. But basically, it just cuts off. You know. Oh, fine, I'll draw it a little bit. So like z equals to top is like this. Right, so basically chop it like that, and then all I'm left with of that infinite, infinite wedge is just that little, four-sided shape right there. But I've also done something. I've described it by a set of inequalities, which then allows us to set up the iterated integral. All right. So again, I have to do the z one first because of the way I've described the region. So I do the z integral first, then I do the y integral, and then I finally do the x integral since it has constant bounds. And since I'm just finding the volume, I just integrate dx, well, in this case dz dy dx. And so you do it, and you get a sixth. But anyway, all right, so. And of course, you could also calculate the average of a function over a solid region. What you do is you integrate the function over the solid region and divide by the volume of the region. So like here I calculate the average of x over that region. So the setup is still the same logic to set it up, and now we just have to integrate with an x here. And so you do these steps, you get 1/24th, and then so like the average, you zoom out just a bit, the average of x over that four-sided solid is 1/4, because the integral is 1/24th, and I divide by the volume, which is 1/6, as we calculated in the previous example. Here is just another just plain Jane, just straight up triple integral, you know, just if you're having trouble with the mechanics of how we iterate the integral, here's another example on like just the integration itself. So I integrate y to start with, which gives me 6xyz. Then I have to evaluate from 0 being y to x plus z being y. That gives me this expression. Then I integrate with respect to z. The first term is, well, I haven't done any integration yet, right? So I get 6x squared z and 6xz squared. So when I integrate with respect to x, rather, that's the next integral. That x squared integrates to x cubed over 2, which gives me 6 over 2 being, hey, wait a minute, x cubed over 3, rather. 6 over 3 is 2. And the x here integrates to x squared over 2, which gives me 6 over 2, which is 3. And then I evaluated the bounds, I get that, and I integrate 5. It ends up being 5z to the 4th after I work it out, and so we get 1. It's funny. All right. So I won't go through all of these examples. I'll just tell you that there are lots of examples in the notes, right? And so, like, you know, the easiest kind of these problems is where you're given the volume already described by a set of inequalities. Then you just have to set up the integration in kind, right? So like this one suggests that I integrate z first and then y and then x. So it's kind of like the most common setup you tend to see. Oh, look, I did it a different way. I integrated, because I could go with y first and then do z and then do x. X definitely has to be the last one, but you could either do y or z, either one before the other. So, and then there's the details, which you can look at. And of course, we still need to know u substitution and all that fun stuff. Now this next example is instructive. It says evaluate this integral in 3 different ways. And so you start with the integration to the region being described, you know, -1, less than x less than 1, 0 less than y less than 2, 0. Oh, this one's easy in the sense that it's just a, this is nothing more than, I'm not drawing it to scale or anything like that, but it's just a rectangular solid, you know. So that means that it's pretty easy to set up the bounds in different order. You know, it's got x equal to, the front side would be x equals to 1, the back side would be x equals to -1, this would be y equals to 2, over here on that side that would be y equals to 0, and you got z equals to 1 on the top, and you got z equals to 0 on the bottom, all right? So this is z equals to 0 down here. And it gets fussy, like x equals to 1. I'm trying to refer to the front face, but oh well, anyway, I tried. So that's the volume we're integrating over here. And one way to set it up, of course, would be to do z first, then y, then x, right? But you could just as well do x first, then y, then z. Of course, when you do that, you'll also get the same answer, right? And if you think about it, there are 4 other ways to evaluate the integral, and each will yield -8. That is essentially Fubini's theorem. So, of course, for non-rectangular solids, the you know, the way to set up the integral can really lead to very different integration steps. Well, that's even true for the last example. Which one you do first makes the integrand easier or harder to integrate. So you got to, you know, maybe choose your battles wisely when you got a choice. This one here, I just want to illustrate the evaluation bar idea. Basically, I integrate x first, so I get xz to the y, and we go from x equal to that to x equal to 0. So that gives me this, so the x equal to 0 does nothing, and x equal to the square root of 1 minus z squared just replaces x with that. Then this is a u equals 1 minus z squared substitution, and then I have the 1/2 power. Integrating 1/2 power gives me 3/2 divided by 3/2, which would have given me 2/3, but the u substitution brings out another factor of 2, which cancels with that 2, and there's a minus because it's 1 minus z squared. So anyway, there's a u equals 1 minus z squared substitution here, if you're wondering, that I haven't written down. And so there it is. Now, another example is here, So I have lots of examples to show you the mechanics of how we do this iterated integral, and you can look at those. And if you find an error or any of them, let me know. It wouldn't be impossible. I did have students transcribe some handwritten notes I had before to this LaTeX, and they made some errors when they transcribed. Of course, my original handwritten notes were free of errors, so it's all in the students. But just kidding. But we found most of them in previous years, but you might find an error somewhere. If you do, let me know. I appreciate it. Anyway, so this one, again, so anytime the region's described geometrically, it requires a lot more work on your part because you have to actually visualize it and then come up with a set of inequalities which describes the region. And then, like, once you do that, you get, once you have all of those together, once you have your 3 inequalities which completely describe the solid region, then and only then can you set up the integration. So this one, I did some visualizing to figure out I had 0 less than z less than x for x squared less than y less than x and 0 less than x less than 1. So the x integration's got to be the last one I do. The last integral you do must be numerical. This is a definite integral. The answer should be a number. If your answer is a variable and it's not like a parameter that appears in the integrand, then you're wrong. You need to go back and do some soul searching and set it up different. You should have a number as the answer here, all right, generally speaking. And anyway, so I did the z integral first, so I put 0 to x for z. I did the y integral second, so I put x squared and x as my lower and upper bound. And then finally the x integral comes last, and eventually you just have well, in this problem, a polynomial in x, so it's pretty easy. We get 2/15. And here again, this example's relatively easy because I described the solid in terms of a given set of inequalities. If you have a given set of inequalities, you should be able to use Fubini's theorem to just set up the integral like that. And then it's straightforward, but it's still integration, to do what follows. So, all right. And I think this one, well, that feels like, I feel like I've seen that answer before. Y is the cosine next to the, hey, isn't this example 6.36? Well, this is like, all right, so notice that this is very similar. This is example 6.36, right? 3 sine 1 over 20 was the answer. Notice that I did the y and then the z integral on the inside. In contrast, 6.311, I did the z then the y integral versus, no, I did zy there too. Wait a minute, no. No, I did yz in the other one. This one I did zy. So I flipped the order of the inside integral and show you that you still get the same answer, although the integration steps are quite different. But you can contrast. You can contrast with example 6.3.6. It's the same integrand, but these guys, I flipped the order of, and correspondingly these bounds are flipped, which makes the integration steps a little bit different, but yet same answer. All right, and then here's yet another one. I like this, I mean, 9 times out of 10, this example or something like it is on my test on multivariate integration. If students can really hack their way through this kind of integration, it shows me they pretty well understand how to do the triple integral. And if you can set it up, this kind of integral, then you're doing pretty well. So I would encourage you to read the problem statement and try to work it out, and then see if you can get the answer without actually just copying the notes down. That'd be a good exercise for yourself. I think I'm sure there's a problem like that in your homework anyway. And here's another cylinder kind of problem. Again, we'll come back to this sort of problem with cylindrical coordinates. It'll be much nicer with that. So And, oh, yowzers. And this one is just a glutton for punishment. Here I have an arbitrary function, and I've set it up using zyx and zyx bounds, right? And here are the 6 different sets of inequalities to describe that one shape. All right, so it'd probably take me 20 minutes to really convince myself that those are actually the other ways of describing that same shape, because it's really a question of sculpting, right? You can take a compact, closed and bounded shape in 3 dimensions, and you can construct it by cutting away cutting away one direction, so to speak, and getting like a slab, and then taking that slab and cutting it again to make it more like a cylinder of some sort. And I say cylinder in the generalized sense of that, but you can cut the slab down so it's only infinite along one axis direction rather than 2. And then you can cut it a 3rd time to take that axis direction and cut it out to something finite, finally leaving you with a a 3-dimensional shape. Now, not all 3-dimensional shapes can be cut like that, right? Generally speaking, a more interesting 3-dimensional solid you won't be able to describe by a set of 3 inequalities. You're going to have to take your 3-dimensional shape and chop it into little blocks, and those little blocks you'll be able to describe by a set of 3 inequalities, and this is by a different set of 3 inequalities. And then you do the integration over this piece, and you do the integration over that piece, and you add them together, right? So that annoyance has been, we have freed ourselves from that in these set of examples, but that is there. Just like with double integrals, you can't always set it up as a type 1 or a type 2. You generally have to parse your area up into a finite sequence of these kinds of pieces, and then and add the integrals of each piece up separately. That's still true for triple integrals. But anyway, I think I'll leave it here. Next up, I think, is, well, lecture 27, obviously, but that's change of variables. So there we'll actually look at how to do this kind of problem in a kind of nicer way. So anyway, thanks guys. Yeah, I'll stop it here.